S of 3. I see, so SO is the same as SU restricted to integer spins. And fib is the same as SO 3. Alright, so be it. So I always Google Parse's thesis, because he has a long list of millions of NM models. And he tells you what all the, he tells you what all the numbers, what all the F matrices are, and what all the R matrices are, and all that stuff.
Kind of awesome.
In the appendix of his thesis. Yeah. Okay, so for general NM model, you have the R move, which is when you switch two things, you pick up a phase. And the F move is this one here. So I have particles A and B fusing into particles E, and D and C fusing into particle E as well. And I want to switch the order, so I want A and D to fuse together into the same thing with B and C. So it switches into this basis, and the coefficient, this is called an F move, and has 6 indices, so A, B, C, D, A, B, C, D, where you're coming from, where you're going to, E to F. Okay, so it's a mess to deal with. With a lot of indices. Every time you do one F move, you already have a lot of indices. Okay, so we talked about this. We talked about the pentagon. The other constraint that we gotta satisfy is the hexagon condition. So the hexagon condition here, let me zoom in. What I'm gonna do is I'm gonna do this operation, okay? So I have 3 particles, and I'm gonna move A across the first 2 into the 3rd position. And I'm gonna do it in 2 different ways. So first of all, I'm gonna do, let's start with, let's do this one first. So first, I move B to the other side, and then I switch A with BC. Makes sense? So I use an F move, and then I do an R move, which is up here. Switch A with BC. And then it looks like I'm doing an F move again, just to get that. Oh, that's not necessary, but just to end up in this fusion picture, fusion order. And here what I'm doing is I'm first moving A across B, and then I'm doing an F move so that A is down there. Then I'm moving A across C. So it's 2 R's and 1 F. And both of these represent the same operation. I mean, at the end of the day, I'm moving A to the other side. So therefore, I should get the same sequence. Whether I multiply the matrices in this order or in this order, I should get the same answer. That's called the hexagon condition. This is the equation written out with all the indices. It's just another expression that every model has to satisfy. But there's a theorem that says if you satisfy the pentagon condition and you satisfy the hexagon condition, then you're consistent for any number of. There aren't any other conditions that you need to satisfy. You're not going to find a contradiction where you do it in one order, you get a different thing than when you do it in a different order. One order of changing bases versus a different order of changing bases, you'll get the same answer no matter what, provided these 2 conditions are satisfied.